Hey folks, welcome back. Um, so let's recap from last week. Last week we started working on this language written in Go. It looks like a scheme for now, which is like a Lisp, simpler than Common Lisp. And posting in chat the repo. But that's what we're looking at right here. So last week we started by implementing Lexer. Let's look at main.go to see how this breakdown. So in a programming language, the very, very basic steps are going to be that we start out reading an input program. We're going to lex it, which is turning that input program, the text of that program, into a bunch of separate tokens. And after that, we need to do steps like parsing the tokens, which turns the tokens, which is just a flat list. It turns them into a nested structure, a tree structure. And after we've got the parsed tokens into a tree, then we can either interpret that AST or we can compile it to a bytecode VM, or we could compile it to C, we could compile it to the JVM. You can compile it to almost anything. But let's go back to the lexing step. So this is what we did last week. If we look at lex.go, right here, we've got, this is an example program. If someone passes this to our interpreter, we want to be able to ultimately we want to be able to produce the result, which is 15. So when you call lex with that program, why is this missing a plus in here? It should produce this broken out text array. So this is every individual important group of strings within the program that we passed in. So you have to group things together, like numbers. 1 and 3 should be grouped together to be 13, but plus should be separate from the open parentheses because plus is an operation, whereas the open parentheses are syntax that says this is the structure of the program. Also, just in case anyone has trouble with the chat, feel free to join the multi-process Discord and message me in there. All right. So this is what we did last week. We were able to lex this kind of string and produce this output. It's a little bit more complicated than that because we want to store information, not just those individual characters from the input string, but we also want to be able to store what kind of token they were, whether they were an integer like 1 or 12, if they were an identifier, which is almost anything else like plus or define. And we also want to store the location because if someone makes a mistake, we want to be able to tell them where that mistake happened. All right, so let's look at the example program that we gave. This looks exactly like the example that we had in the code. So if we build our program and run it against that example, all we did right now is print out these tokens just using Go's built-in printer for these. So it's not very pretty, but so let's make this a little bit prettier. All right. So rather than printing out all the rest of the stuff, which included like the token kind and the location, now we just printed out the actual value. So you can see that we're lexing this correctly. So the next step, like I said, according to this main.go, after we've got these tokens from this input string, we need to be able to parse out the tokens into a tree. And so let's make this example a little bit more complicated. If you look at that example, So in this case, what we're the tree structure is going to look like this. Got plus here, got 13 on the one side. This is the way that we want this to look once it's a tree. So we've got plus at the top, and the two operands are 13, and then the result of subtracting 12 minus 1. So right now we don't have that structure. If we print this program, let's get rid of these because we didn't implement comments yet. It's just this flat structure. So parsing needs to go from that flat array of tokens to this structured thing, structured tree. So let's open parse.go. We had lex.go for doing lexing, and we'll do parse.go for parsing. Lex returns this array of tokens, so parsing is going to take an array of tokens, and it's going to produce an AST. This AST, let's think about that. So ASTs in anything in Lisp and Scheme are pretty simple because it's always just an array of arguments, any of which may also be arrays. And one way that that's expressed commonly is with car and cdr. These are Lisp terms, meaning the first in the list and everything else. So when we have this, let's do another example like we did for the lex function. When we call parse on this, yeah, let's do the more complicated example, 12 and 1. We want this to look something like this. Bum, bum, bum. Actually, you know what? I don't know if this is going to be the easiest way to do this. Let's see. It's been so long since I implemented a list, but I do always find this part confusing. So I'm just going to have to play with a couple different things, and we'll see which one makes the most sense. Let's see. How else can we do this? If everything is an AST, and I'm not typing go here. I'm just thinking out loud. If everything is an AST, then this could look like this. All right, this makes a little bit more sense. And then these don't have to be called. Um, so if we call these values and a kind is a literal, these all must be the same one. So this one would be list. All right, this makes a little bit more sense. I think that we could have gone this route, but that's just going to be more complicated. So let's do this one where where AST is just a, let's switch back to Go mode now. AST is just a list of values. Maybe let's uh, kind and literal is one kind. This can just be a token, and the other one is a list, and this one is a list of, or this can point back to AST as well, since that's a list of values. So let's define value kind. This is going to be another enumeration, just like we did in Lex for token kind. Const, what are the kinds? Literal kind and list kind. Okay. So let's add back this comment here. All right, so again, let's comment all this out. All right, so when we get a string like this, once it's Lex, it'll be this array. And this should produce an AST, which is a list of values. And the values, the tree structure that we're looking for is this, where the first one is going to be plus, next one is going to be 13, the next one is going to be a list, because just like here, every time we have parentheses, that's a list. So the kind of this one will be list. Inside of here, the first value in the list will be the minus, the next one will be, oops, the next one will be the 12, next, and the last one will be a 1. So that's it. Parsing should be able to take this array of tokens and produce this structured tree. And the tree is always going to be a list of values, and the value can either be a literal, which is going to point at one token, or it can be an array of values. All right. And already you can see that this stuff blows up. Like you start with this really compact array. You start with this really compact program here, and Lexing turned it into an array of tokens, and the tokens are bigger than these strings because, like I already said in the beginning of this video, the tokens include, let's look at that. The tokens include the value itself, which is the string of what the token is. They include the kind of the token, and they include its location. And now parsing is going to blow this up even further because we're going to produce this massive tree. All right. Now that we know what we're aiming for, let's go ahead and try to do it. So let's just start sketching here, and we may refactor as we go. We're definitely going to want to be iterating through the tokens. We're also going to want an AST that we actually produce. And so inside of here, the big thing that we need to care about is if the token is a syntax token, and if it's an open parentheses or if it's a closing parentheses. If it's an opening parentheses, then we need to parse recursively. We're going to get this wrong, but let's just give it a shot here. And all right, rather than going through these token at a time, we need to do like what we did with lexing, and we need to just go. We need to have an index that's tracking these. So index. And this means that parsing is going to have to return not just an AST, but an index, just like we did with lexing. And the reason that you need to do that is because you can't just iterate through each token one at a time when you're going to be calling out to something that can consume any number of tokens. And when you have to recursively parse another list, you're going to be consuming, you don't know how many tokens you're going to be consuming. So every time that you go recursive, you need to know what the next index is. And if we're going to be calling this with an index, that means it's going to have to accept an index. So we can get rid of this, actually. And we would want to make sure that like there should be some error handling here, but potentially we could just panic if there's an error. So we don't have to worry about an error right now. Just something to think about in the future. And if there's no error handling, that means that what we can do is we can immediately accumulate the child into the AST. And we can set index equal to next index. So if we, why is that complaining? Child. Okay. So the problem here is that we called parse, and parse returns an AST, but AST is an array of values, not ASTs. So how are we going to solve that? I don't know. We'll think about that. But as I was saying, if opening a parentheses means you go recursive, the ending case for that recursion is the closing parentheses. So here is a case where we're going to want to return early and return everything that we've accumulated in terms of the AST and the current index. Possibly +1. This we'll have to deal with in tests, or we'll just notice it because it'll infinitely recurse. So we'll figure that out in unit tests. Okay, so if it was one of these two cases, then we're either going to... Oh, do we continue here? Yeah, probably. I think we continue. If it was an opening parentheses, we need to go recursive and recursively parse so that we can get a new tree to put in line with the rest of other tokens. If it is a closing parentheses, then we know that that's the end of recursion. But otherwise, it's just the normal case of a thing that's in a list that's just a literal in an array of literals or an array of AST values. And here we just accumulate that. We need to wrap it. Kind, kind, literal kind. This is tokens at index. And I think that shows me also why this is wrong. So we always have to wrap this, and this wrapped one, the kind is going to be a list kind. There we go. So yeah, that worked out. And if we get to here, and if it's just a literal kind, we need to increment the index. So why are you complaining? Syntax token. And actually, this is. Oh, okay, yeah. So there are some edge cases that we'll want to test, but actually we finished with the parser. This is kind of why lists and S expressions are popular, because that's it. Now, undoubtedly, we got something wrong, but let's still. Oh yeah. So here, I think we might want to do a +1 here, because when we send in the next token, we don't want to include this opening parentheses. Yeah, let's try testing this. So our test table in this case, again, like it said, with that, this is going to be hairy. It's really bulky to test, so it might help if we have a test helper, or if we only test that the token values match up. So let's sketch out what some tests might look like. Input, it'll be easiest if it's just a string, and output. Yeah, let's say that the output is an AST, but let's try to not fill in everything, because that's just going to take forever. So let's just do some simple ones first. This one, there's no recursion inside of parse. We'll just call parse once, and the reason I say that is because there's no nested parentheses. In contrast, if we have this one would have recursion inside of it, because it has to go call parse again once it gets here. But let's comment this one out for now. Well, let's add some more, and we'll comment them out so that we can deal with the easy ones first. That's potentially a special case. This, syntactically, that doesn't make sense, but it's also common to not do, because this gets evaluated at runtime, that's kind of when, so I guess syntactically it does make sense. Just at runtime, it would blow up. But we're not evaluating anything yet, so this is fine. And the reason I say this would blow up is because in Lisp or Scheme, the thing that is the first one in the list is a function, basically. And while it would be fine to evaluate this, this is going to produce the result of 3, and 3 is not a function. But anyway, I guess at this point, we've just ascertained that it should parse successfully. It just won't produce the right result. So let's fill these out now. This one should be... Okay. And let's show you what these ones look like. First one is still plus, second one is still 1. This one is a list. And inside of it are the minus, the 12, and the 9. Yeah. Guess I can make the font a little bit smaller. Hopefully that's still readable. But the indentation is wrong. No. All right. So that was negative, and then 12, and then the last one inside here is going to be 9. So again, hopefully you see this tree structure we've got here. But let's comment this out, and let's comment the other ones out, so that we don't have to deal with them, because I probably got something wrong. Let's just try the basic one first. All right, so now that we've got that filled out, let's do the actual tests. First, we need to get the tokens. Then we're going to try to parse the tokens. And now we need to do a compare. Compare the AST. All right, so we'll implement this compare ourselves so that we don't have to worry about the stuff that was left unfilled out. So in a token, as I already said, tokens have 3 fields. We didn't fill those out because we're just writing a test and we want to be easy. So in our compare function, we just won't check all those fields. Compare AST. Cool. Insert dot true. All right. A AST and B AST. So if all right. And let's do a compare value function for each of these. If not false, turn. All right. So there are other things that we could have checked. Oh, no, wait. Yeah, it doesn't work like that. If a.kind equals literal, And what is your issue? Parse echo. Literal, yeah, kind. It would be fine to call them kind, but it's just in the go to the lexer when we define these enums here, we call them syntax token, token kind, syntax token, integer token, identifier token. All right. Back to the tests. Literal value is now defined. Otherwise, if it's not a literal value, it must be a list value, so we can return there. Let's give it a shot. Oh. Wait, no, we can't do that, what I just did. We can't just compare the lists directly with equality, because the version that comes out of the parse will have a full token, which includes location, and ours didn't. So here we need to do our compare st function. A.list, b.list. And why are you complaining? Because it is a pointer to an AST, not an AST itself. All right, let's try building first. Oh, build, that's good. Let's try testing. Line 46, literal kind. Okay, yeah, I just renamed those. Literal value. Not enough calls to parse. Right, we need to tell it where to start. All right. That's not very helpful. So let's print something out. Let's first print out the input, and let's print out the tokens. So the input was +1 and 2. And this already looks like it has stuff that we don't want in there. So let's go back to the lexer test. We only had one lexing test in here. Let's add another one. So this is the good thing about having unit tests for this stuff, because we printed out the tokens and they're oh no. Okay, wait, no, sorry. The first token, yeah, it should be a left parentheses. So there should be 1, 2, 3, 4, 5 tokens, and yeah, there are 5 tokens. All right, I was getting mixed up for no reason. So the lexing result looked reasonable there. So that's where we printed this. Now let's print out the AST. And this is not going to be pretty. So let's implement a prettifier for this. Parse, go. And this will be p plus equals value.pretty and then return p plus. So we just want to be able to print out the parsed AST back as an S expression. So we've got a pretty implementation for the AST. Now we need to do the same thing for the value. If behind literal, then we can just print out, we can just return the literal's value, which is a string. Otherwise, we can return the list pretty. All right. Spaces in between these would be nice. So that's this right here. Just doing it one more time with print line, not print. All right. Yeah, so this is weird. Why are there parentheses? Why does it have nested parentheses here? And so yeah, that's interesting. Let's make a special case that says that token.index must be this. If tokens index, let's copy this condition. Why are you complaining? Yeah. All right. This makes sense because every time we call parse, we do want to be starting with an open parentheses. And that also means that in this case, we probably should not increment it, the index, when we're going recursive, because we want, once we see an open parentheses, now that we made the check that says we have to see the open parentheses, we're going to need the index to stay the same here. Let's try that out. All right. And we probably just had infinite recursion, but let's see. Yeah, this looks like infinite recursion. Yep, this happens to me every single time. And the reason is going to be because it's these index incrementing. We need to figure out the right way to increment the indexes and where we're going wrong. And actually the weird thing though is, okay, well maybe that was obvious. It should be here. Yeah, because if we didn't have this, every single time we'd be going into this case and recursing and going back into that case. All right, so we figured at least one of the recursion issues. And the reason that that was so obvious was because in this case, this test that we've got here, there is no recursion. There's only one left parentheses. It's not going to call parse any more times. Okay. So that test still failed. Why did you fail? Now that we've got that pretty function, though, we could also do a simple check. Like this, so that we could just do a very quick check before we do this full compare AST thing. But that's not going to be super helpful in this case because we already know that the compare AST is the part that's failing. Test.pretty. So if we run this again, I think it's just going to fail the same thing. All right. Let's just add print statements to figure out where it's going wrong. Value kind not equal. Lengths are not equal. Value is not equal. This is going to have some redundant prints because if we're printing here, we probably also printed here. So yeah, let's get rid of this. And there are some other cases like here that will not be printed out if this is false. So let's try this, and maybe some of the prints that we've got will be relevant. Nope, they're not. So let's do... All right, there we go. We got that the literals are not equal. Now why are... Oh, okay. Because we tried to compare it. So literal is a whole token, and that's not what we want to look at. We only want to look at their value. All right, cool. So that's reassuring. The basic, the simplest version of this parser where there's no internal recursion, that's working. Now let's try one with actual recursion. So let's uncomment this. And let's add the pretty output version of this. And let's give it a shot. List kind. That should be list value. Oh, wow, it worked. That never happens. Cool. Let's uncomment the others and add them. Their test, the expected result for them. So the potentially special case here is that we have more siblings for this outer list after we finished recursion on this inner one. So the pretty version just has these extra spaces in here. And the only difference between this one and the previous one was that there's a 12 at the end. Let's give us some more screen space here. Yeah, here. All right. That one looks good. Let's try running those tests. All right, that one worked too. And the final one. We'll copy the same expected result, and we just need to change the first value. So this first one is no longer a literal, the list. And let's copy this. All right. Yeah, so the only difference between this and the previous one was that instead of this first value in the list being a plus, it's now an expression itself. And that works too. Wow, that's awesome. The first time that I tried to parse S expressions, I was stuck for days or weeks. So if you go and try to do that yourself and you get stuck, that's totally normal. Maybe it's just luck, or maybe I've had some practice. All right, so now that we have that done in main, we can uncomment this. And we can pretty print the AST. and we build, run this against that example. Let's look at that example again. All right, so if we run against that example, these were the tokens printed up here, and this was the parsed AST printed back at us, and it looks correct. All right, that's pretty good. So recapping, we needed to go from an input program, and we needed to get the exact structure of that input program. So in Lex, we went from an input program string to an array of tokens. And in parse, we went from that. I didn't. Where's that comment? There it is. Just copy this comment to the function. All right, so Lex, we went from an input string to an array of tokens. Parse, we would go from an array of tokens to this tree. And now, back in main, when we pick this up next week, we'll be able to implement interpreting over that tree. And there are tons of different ways that you can do this. You don't, just taking a step back, not all programming languages have these separated steps. Some go directly, some don't do this breaking out into tokens. Some don't have a parse step where they produce a tree. There is this one example, I think it's Brian Callahan. I can never remember the guy's name, but there was this series on Hacker News that was writing a compiler in C, and his did not produce any AST at all. He just went directly from input to compiling output. And you can do that. And it has the advantage of when you're building an AST, you have to deal with the memory of the AST. In Go, that's not really a challenge because it's garbage collected and they just let us create memory easily. But in C, which is the language that guy chose to do his in, it's easier because you don't have to deal with the memory for the AST. But this is a pretty useful stage, this lexing and the parsing stage. So every time I go to implement a programming language, that's what I do. In most production parsers that implement handwritten parsers like we're doing here, they'll do the same thing. So this is a really common pattern, but it's not necessary. You don't need to do this. And the term that you might want to look up is one-step compiling or one-stage compiling. If I remember to look it up and if I can find it, I'll share a link on the YouTube video for this one that's up. But yeah, that's it for this week. We've got parsing done, and next week we'll go into interpreting, which is going to be more fun and more challenging because S expressions are just so easy to parse. They just take so little time to build a parser for it. I think we did it here in like 30 minutes. It's just after that, you need to deal with like, how do you deal with function definitions? How do you deal with calling functions? How do you deal with the values? It's going to be easy because we're in Go and it's garbage collected, so we don't really have to think about a lot of that. But yeah, that's up next. Thanks, everyone.